Hi everyone, welcome to goclasses. In the last lecture, we were discussing memory interleaving. Yes or no? Memory expansion we were discussing. So let's see the recap of this memory interfacing, or you can say memory interleaving, or you can say memory expansion. Okay. So these are the different, I can say terminology, and these are similar concepts. Okay. Memory interleaving, or I can say memory interfacing. Okay, so let's see the recap of this memory interleaving that we have already seen. We have seen the structure of memory device. Okay, this is the first thing that we saw, that the memory device, basically what it has. Memory device, you can easily see that there are some address lines. For example, you can see in this memory device, there are total 8 addressable locations. You have total 8 locations. Okay, so I can say there are total 8 addresses here. Okay, yes or no? So we need 3 bits in the address. Okay, so basically, if you want to address this memory, then you need 3 bits you need in the address. Okay, so you can see there are 3 address lines here. There is an address decoder. Okay, and you can also see there are data lines. For example, let's assume one word equal to 1 byte. Okay, so you can see here you have total 8 data lines. Also, you can see that there are 3 other inputs. Okay, 3 more inputs are there in this memory device. In this memory device, we have read enable, write enable, and there is a chip select. Okay, so these are 3 more inputs in a memory device. So overall, if you look at a memory device overall, then what you will find, if you see the memory device, let's assume this is your memory device, let's call it RAM. Okay, so this is your memory device. In this memory device, what you will have address lines. Okay, so I am saying that these are the address lines. Okay, or I can say these are the address lines, or you can say address pins. Correct. Okay, so there are some address pins, there are some data pins, correct. Okay, data lines, or you can say there are some data pins. You can say data lines, or you can say data pins. Similarly here, address lines, or you can say that there are some address pins. Okay, now what else we have in this memory? In this memory, we have 3 more inputs. Yes or no? So there is a chip select, you have a chip select, and there is a read enable, and there is a write enable. Okay, so these 3 more inputs we have. This read enable, this is also called, you can also call it output enable. Okay, so these are different names for read enable. So you can see what is this. This is your read enable. You can also call it output enable. Okay, is this clear? So you can easily see. And what this bubble indicates, this bubble indicates active low. Okay, this bubble, this indicates active low pin, active low input, or you can say active low pin. Okay, so very simple. So this is these are your active low pins. Very simple. Okay, remember one more thing, that these pins, they can be active high also. In the GATE exam, they can give you, it is possible that they can give you that these are active high. Okay, so that is also fine. Okay, whatever they give you, you can handle it. So right now you can see usually they are active low. Okay, this I told you already, that these pins, if you look at these pins, so if you look at these pins, for example, which pins? These read enable. Okay, these read enable, write enable, and chip select. Okay, these pins, if you look at these inputs, if you look at, these are usually these are active low, okay, but they can be active high also. In the question, they can give you that these are active high also. Okay, that is also possible, but usually these are active low. Okay, now you tell me, if these are active low, then what are the functionality of these pins? So first of all, you notice this is your overall memory structure. Okay, this is the overall memory block diagram. Okay, in this memory block diagram, there are data pins, there are address pins, and there are 3 more pins. These are control pins. Yes or no? Okay, these are your control pins. You can say that these are the control pins. Okay, these pins, you can say that these are basically the control pins, or I can say these are control lines. You can say these are the control lines. Okay, now, so what is the working, or I can say what are the behavior of these pins? Tell me, what is the functionality of these pins? Very simple point, that if this pin, for example, this chip select, okay, if this pin this is your chip select pin. The name of this pin is chip select. We have already seen this. Okay, this you can see chip select, CS. So CS means chip select. You already know CS. What that means? That means chip select. Okay, so you can see this is this chip select. This is active low. Yes or no? This is active low input. This is active low input. Means when this is low, then it will be active. Okay, means when this is low, when this chip select, when I apply 0 here, then this RAM will be active. Okay, is this clear? When I apply 0 here, this input 0, if I apply this input 0, then this RAM will be active. So you can easily see this chip select. If I apply 1, then there will be no working. Okay, in this situation, what will happen? In this situation, your chip, your RAM is idle. Okay, your RAM is inactive. Your RAM cannot do any functionality. I can say this is idle. Okay, all the connections, they will not work. Yes or no? Okay, so very simple. So this is the idea. But you can see this chip select, this is active low. What it means? It means when it is 0, then chip will be active. Okay, then your RAM will be active. So when this chip select is 0, now in these situations, when the chip select is 0, in these situations, what will happen? That this RAM will be active. Okay, is this clear? Now let me also write here read enable, or maybe what I can do, this chip select, let me write here chip select. Okay, and let me write the remaining, for example, your read enable and your write enable. Okay, so you can see when chip select is 1, then your chip is inactive. Your chip is inactive. Your chip will not work, because remember this chip select, this input, look at this input. This input is active low, means when this is 0, when you apply 0, then this will be active. Active low means when it is low, then it will be active. Okay, this chip select, when it is low, then it will be active. So when this chip select is 0, when you apply 0 here, then this RAM will be active. Otherwise, if you apply 1, if I apply 1, then this RAM will be idle. This RAM will be inactive. So this is what you can see. Okay, so when chip select is 1, then this RAM, this will be inactive. It does not matter what you apply on the read enable, what you apply on the write enable does not matter. Okay, they don't care. What this symbol means? This cross means 0 or 1, don't care. Basically, this cross means don't care. Okay, this cross means don't care. Don't care means this can be 0 or this can be 1. Whatever you want, you can put here. Okay, now if this chip select is 0, now what will happen? In these situations, I can say that memory is active. Okay, memory activated. This memory chip is activated. Okay, so this will be activated. Now you can easily see that read enable, write enable, these are also active low. These signals, these inputs, these are also active low. So when they are low, then they will be active. Okay, so you can easily see that if I apply 0, 1, now what it means? You can see when this is 0, when this is low, then it will be active, because you can see these inputs, read enable, write enable, these are also active low inputs. So when they are low, they will be active. Okay, so when you apply 0 here on the read enable, if you apply 0, so you can see here, if I apply 0 on the read enable, on the write enable, there is 1. Now in this situation, what will happen? Memory read will happen. In this situation, memory read operation will happen. Okay, memory read operation happens. Next, you can see if I make this write enable 0, okay, and read enable 1, now what will happen? Now write will happen, memory write will happen, because this write enable, this input is active low. Okay, this write enable, this is active low, means when it is low, then it will be active. Okay, when you apply 0 here, when you make it 0, then what will happen? Then writing will happen in this RAM. Okay, so memory write will happen. In this situation, memory write will happen. Okay, memory write operation will happen. Very simple. Okay, is this clear? And one more thing, that this case is never possible. Okay, when you are making basically read enable, write enable, both of them you are making 0, this case is never possible. This case will never be possible. Okay, we will never make both of them 0. Read enable, write enable, we will never make both of them 0. Okay, so this case is never possible. Very simple. Now remember one thing, in the GATE exam, they can give you that it is possible, they can give you that these pins, they are active high. Yes or no? They can give you this type of diagram, and they can say that these pins are active high. Okay, is this clear? This is also possible in the GATE exam. They can say that these pins, they are active high, or maybe they can simply say that chip select, that is active high. So basically whatever they give you in the exam, they can give you. Okay, let's assume that these pins are active low, but this is active high. Okay, let's assume. Okay, here you can see this chip select is active high. This chip select is active high, and this bar indicates what? Tell me. This bar indicates what? This indicates active low. Okay, these are active low pins. These are active low inputs, or I can say these are active low pins. Okay, so you can see this bar indicates active low. Okay, so here I'm saying that chip select is active high. And of course, what else you have? In a RAM, what other pins you have? Tell me. In this memory, what other pins you have? There are address pins. Okay, there are address pins. So you already know there are some address pins are there, and there are some data pins are there. Okay, there are some data pins. Okay, so this is the overall structure. Now you tell me, in this situation, when your chip select, this chip select is active high. Okay, this is your active high pin, or I can say active high input. Now in this situation, when this memory chip will be activated, here you can notice I am assuming that chip select is active high. What that means? Chip select is active high. This chip select, this input is active high. This input is active high. What that means? That means that when chip select equal to 1, then this chip will be activated. When chip select equal to 1, then this chip will be activated. Then this memory chip activated. Okay, then it will be activated. Okay, very simple. Okay, so you can see this is active high, means when it is high, then it will be activated. When this chip select, okay, when you apply 1 here, when I apply 1 here, then this RAM will be activated. So very simple. Now you can easily make a diagram. Okay, this type of table you can make: chip select, and of course you have read enable, you have write enable. Okay, and what is the activity, what is the action that will happen, that you already know. This chip select is active high. What that means? This chip select is active high. Okay, this is active high. What that means? When it is 1, then action will happen. Okay, when it is 1, now the memory is activated. Now the memory chip activated. Okay, in this situation, memory chip will be activated because chip select is active high. Okay, clear? Very simple. When it is 0, then whatever signal you apply here, this memory chip idle. Okay, this memory chip idle, inactive. This memory chip is idle. Okay, very simple. And when it is 1, then functionality will happen. Then normal function will happen. Means, for example, if it is 1, remember this read enable is active low. Okay, this read enable, this is active low. I am telling you, I have given to you that this read enable is active low. Similarly, this write enable is also active low. These are active low. Okay, these signals, these are active low signals. So you can see when this is 0, then memory read happens. In this situation, memory read will happen. And okay, and similarly, if this is 0, then memory write will happen. Then memory write will happen. So very simple. So this is the idea. I hope you understood. Okay, now let's move on. So we have seen all the things we have seen what is read enable, what is write enable. Okay, we have seen what is address decoder. This address decoder also we have seen. All these concepts we have seen. We have seen what is chip select. Okay, you can see this concept also we have seen. The chip select, this is active low signal. Read this chip select. What is that? This chip select is active low signal that enables or disables the memory device. Okay, very simple. So this is active low, means when it is low, then it will be active. So you can see when chip select equal to 0, when you make chip select equal to 0, then memory will be active. Then memory will transfer data. Then memory will be active. If you make chip select equal to 1, then memory will be idle. Okay, then memory is inactive. Very simple. Okay, so this is the concept. Now let's move on now. Okay, so we have seen this chip select. All these things we have seen. Okay, now you can see if you have four memory chips, then what are the allowable settings? If you have 4 memory chips in your computer, there are 4 memory chips. So if you have 4 memory chips, then what are the allowable settings? So you can see these are the allowable settings. For example, if I make this chip select, this CS0, if I make it 0, then what will happen? Then memory device 0 is connected. Then memory device 0 is activated. Okay. In this situation, memory device 1 is activated because chip select, that is a active low signal that you already know. Okay. So very easily. So if I want to activate this last memory device, if I want to activate this memory device, then what I will do? Then I will make this chip select equal to 0. All other chip select, I will make it 1. So in this situation, what will happen? This memory device 3 will be activated. Okay. So very simple. So all these points, all these concepts we have already seen. Now let's move on. Now we were discussing memory expansion. This concept we were discussing. And I told you there are 2 types of memory expansion. What are those? One is horizontal expansion, another is vertical expansion, right? Yes or no? In the horizontal expansion, what we do? Tell me. So this memory expansion, this topic we have already seen in the previous lecture. So tell me, this memory expansion, there are 2 types of memory expansion. Basically, you want to create larger memories. Okay, you want to build larger memories, so you can do memory expansion. Now, there are 2 types of memory expansion. One is horizontal, another is vertical. In this horizontal expansion, what we do? In this horizontal expansion, basically we increase the number of bits per location. Yes or no? So in this horizontal expansion, what we do? We increase the number of bits per address location. On every address location, we want to increase number of bits on every address location. In this vertical expansion, what we do? We increase the number of address locations. We increase the number of address locations. Okay, very simple. Is this clear? So in the horizontal expansion, we increase the number of bits per address location. And in the vertical expansion, we increase the number of address locations. Okay. Or you can simply say that in vertical expansion, we increase number of words. And in horizontal expansion, we increase the word size. Okay. So this is the idea. Now let's move on. Now let's see horizontal memory expansion. I told you this is not interesting and this is very simple. Okay. So there is, I can say, nothing tricky in this horizontal memory expansion. If you want to increase number of bits per address location, then you can use horizontal memory expansion. For example, consider this example. Implement or design a 2K byte memory using 2K by 4-bit chips RAM. Now you tell me, in this question, you read this question and tell me, is this example of horizontal expansion or vertical expansion? Tell me. This is example of horizontal expansion or vertical expansion. So remember, you want to implement 2K bytes memory using 2K by 4 bits chip RAM. So this is horizontal expansion. Yes or no? This is what you want. Basically, this is what you have. Okay. Basically, using 2K by 4 bits. Okay. These RAMs you have, these RAM chips. These RAM chips you have. Using these RAM chips, we want to design. What we want to design? We want to design 2K bytes. Okay, I can say 2K by 2K by 8 bits. This RAM chip we want to design. Okay, this memory chip we want to design. Is this clear? So very simple. Now, this is the example of horizontal expansion. Okay, because this 2K, they are same. 2K, they are same. The only difference is this. This is the only difference. Okay, so basically what we want here, at every address, we want to increase the number of bits. We want to increase number of bits on every address. Okay, so this is your horizontal expansion example. Okay, this is the horizontal memory expansion. Memory expansion example. Okay, and this is quite simple. I told you this is very simple. First of all, remember what chip you have. These chips you have, and in these chips, you tell me. So this is the block diagram of these chips. Okay, these are the chips that you have. In these chips, you can see there are 4 data lines. Yes or no? In these chips, how many data pins are there? Okay, in these chips, in these RAM chips, how many data lines are there? So there are total 4 data pins. Yes or no? I can say like this, that there are 4 data pins. 4 data pins are there, right? Yes or no? Okay, what are those 4 data pins? let's call them D3 to D0. Okay, let's call them D3 to D0. So these are the data pins. Now tell me, how many address pins are there? How many address pins are there? Let me know. Total 11 address pins are there because 2K locations are there. You have 2K locations. So there are total 11 address pins. There are total 11 address pins. Okay. Quite simple. There are total 11 address pins and there is a chip select. You already know. Okay. There is a chip select, your favorite chip select. Read enable, write enable. Those also you know. Read enable, write enable. Okay. So this is the block diagram of these chips. And what chip you want? Tell me what chip you want. What type of chip you want? In what is the only difference? Just tell me. Just tell me what is the only difference. Let me know. The only difference is in the data lines. Yes or no? The only difference is in the data lines. How many data pins you have? So basically now what you want total 8 data pins. That's it. Total 8 data pins you need. Okay, means from D7 to D0. This is what you need. Only data pins you need to change. Everything else is same. Yes or no? How many address pins will be there? How many address pins? The same 11 address pins because 2K locations are there. Because you have 2K locations, the number of address locations you did not change. So same 11 address pins, same 11 address pins. Everything else is same. Okay. The only change is 8 data pins. Total 8 data pins you need. But how many data pins you have in these chips? In these chips, you have total 4 data pins. Yes or no? So what you can do? You can do horizontal expansion. In this horizontal expansion, basically what you will do, 2 chips you will put here. Okay. These 2 chips, these are the memory chips. These 2 chips you will put. And what you will do? Somehow what you will do basically, what you will do, let me tell you, whenever some address will come. Okay. Let me tell you the idea. First, let me tell you the idea. What is the idea? The idea of horizontal expansion is this, that here you have 4 bits, right? Yes or no? Here you have 4 bits. Okay. Here you have 4 bits because 2K by 4. These are the chips that you have. Yes or no? 2K by 4. These are the chips. 2K by 4. These are the chips you have. This is also 2K by 4 chip. This is also 2K by 4 chip. This is also 2K by 4 chip. So there are 4 bits here on this address. Okay. Let's assume this address is, okay, let me call it this address. Let me call it, for example, maybe 40. Okay. Let's call it address 40, or maybe you can simply just, okay, anything does not matter. Okay. Let's assume this is address 60. Now you can easily see that this is your data. Yes or no? Here also you have some data. Okay. Now, what is the idea in the horizontal expansion? In the horizontal expansion, the idea is this, that basically these 2 will act as one location. Yes or no? This will act as one location. Yes or no? What we will do? We will make it in such a way. Okay, we will make it to act as one location. Yes or no? As one address location. Is this clear? As one address location. So very simple point, that what we will do in the horizontal expansion, what we will do, this basically, these are two different chips, remember. Okay, these are 2 different chips. Let's call it chip 0, let's call it chip 1. These are 2 different chips. But what we will do, we will do something such that these 2 addresses, this is also 60, this is also 60, we will make it to act as one address location. Okay, is this clear? So this complete thing will act as one address location. Okay, so how to do that? Very simple. How to do that? Whenever some address will come, whenever this address will come, let's assume CPU has generated some address. Okay, whenever this address will come, you know, address is total 11 bits. You already know. Okay, because you can easily see that address, that is 11 bits. Okay, total 11 address lines are there. So whenever some address will come, let's assume this address has come, then remember this same address, what we will do? Okay, this same address we will send to both the chips. Okay, using this address, this location also will be activated, and using this address, this location also will be activated. So what we will do? We will send this address, or I can say using this address, we will activate both these locations. Okay, both these locations we will activate. Then what we will do? Now what we will do? Remember, there is a chip select. I told you, yes or no? I told you there is a chip select. Yes or no? There is a chip select. So let's assume this is, for example, maybe this is the chip select. This is the chip select. Now what we will do? We will connect these two chip selects. Agree with me? Yes or no? These two chip selects we will connect. Now what will happen? Just tell me one thing. Now if I activate this location, means if I activate this memory device, memory chip, then this memory chip also will be activated. Yes or no? Please tell me, did you understand? Okay, these two chip select, I will make them one, I will connect them. Okay, so now when I activate this memory chip, then this memory chip also will be activated. That's it, very simple. So this is the complete idea. Now what I will do? Total, remember how many data lines I need? Please understand, I need total 8 data lines. Okay, this is what I want. This is what I want. I want to design this. So total 8 data lines I need. So what I will do? So remember, I have total 8 data lines. Okay, total how many? I have total 8 data lines, D7 to D0. And from where these 8 data lines will come? Very simple. The 4 data lines, what I will do? These 4 data lines that you have here, I will consider them as MSB. Okay, so these 4 data lines, remember, these 4 data lines I will consider as MSB, and these 4 data lines I will consider as LSB. Okay, these 4 data lines I will consider as LSB. So this is the idea. Okay, these data lines and these data lines. Okay, so very simple. Is this clear? So remember, these data lines that you have, like these data lines I will consider as, they will work as LSB bits. And these data lines that you have, these data lines D3 to D0, they will work as MSB. Okay, they will work as MSB. They will work as MSB. Okay, so I hope you understood. Please tell me, did you understand? So very simple. This is your horizontal expansion. Okay, understood? Let me know. Please tell me. Okay, so this is the idea. So horizontal expansion is quite simple. There is nothing fancy. In the horizontal expansion, remember, the only thing what you need to do, the horizontal expansion. Okay, so let's see in the horizontal expansion what you need to do. Very simple. No decoder required. Yes or no? No decoder required. No extra decoder, basically. No decoder required. You don't need any decoder. Okay, this is the first thing. No decoder required. Basically, just you need extra data pins. Yes or no? We just need more data pins. We just need more data pins, more data lines, or I can say data pins. Okay, so we just need more data lines. That's it. Nothing else. We don't need anything else. So this is your horizontal expansion. Okay, very simple. So there is nothing fancy here. Basically, in the horizontal expansion, there is nothing fancy, or I can say very simple. Yes or no? This horizontal expansion, this is very simple, nothing fancy. Okay, and remember that address lines will be unchanged. Yes or no? Address lines unchanged. Correct? Okay, address lines unchanged. There is no difference. There is no changes in the address lines. Address lines unchanged. Okay, so these are the things. This is the complete summary of horizontal expansion. So in the horizontal expansion, basically, these two locations will act as one location. They will act as one location. They will act as one address location. And how they will act as one address location? I told you, because what we will do, we will connect their chip select. This memory chip, this memory chip, this is your chip 0, this is your chip 1. What we will do? We will connect their chip select. So when you activate this chip, then this chip also will be activated. Basically, both of them will be activated simultaneously. Okay, and the same address will activate this chip also, this chip also. So when the CPU will generate the address, then this chip also will be activated, this chip also will be activated. Okay, and finally, these are the data lines. These are the data lines that we need. Okay, so very simple. So this is the final idea. Okay, let's move on now. Now let's see vertical memory expansion. This is interesting. Okay, and remember, in the GATE exam, many questions will I can say many questions have come on this vertical memory expansion. This is interesting and many good questions can be created. What is this vertical memory expansion? Basically, you are increasing the number of address locations. Okay, this is what you are doing. Number of address locations you are increasing means number of words you are increasing. Okay, very simple. Now, for this, if you want to increase number of address locations, means when you want to do vertical memory expansion, then memory interleaving is used. We have already seen in the previous lecture. Do you remember? Memory interleaving is used. There are two types of memory interleaving. One is high order memory interleaving, another is low order memory interleaving. These two concepts we have already seen in the previous lecture, but let's see one example. What is high order memory interleaving? Tell me, what is the definition? What is the definition of high order memory interleaving? In the high order memory interleaving, basically, the high order bits are used to select a chip. Yes or no? Okay. Remember, we are discussing vertical memory expansion. Means we want to increase the number of address locations. So we need multiple chips. We need many chips. Okay. Yes or no? We need many chips. If you want to increase number of address locations, then you need many chips. This is your vertical expansion. This is your vertical expansion. This is the vertical expansion. So here what you need many chips. For example, maybe this is your chip 0, chip 1, chip 2, and this is maybe your chip 3. Correct? Okay. Chip 1, chip 2, and so on. So these are the chips. So very simple that in the vertical memory expansion, if you want to do the vertical memory expansion, then memory interleaving is used. There are two types of memory interleaving. One is high order memory interleaving, another is low order memory interleaving. In the high order memory interleaving, what we do? We use the high order, means MSB bits, to select a memory chip. Okay, MSB bits of the address are used to select the memory chip. So this is the definition. Read this. Okay, high order memory interleaving. In this, what we do? The high order bits means the MSB bits of the address. They will determine the chip. They will be used to select the chip. So remember, most significant bits of the address, MSB bits of the address, will be used to determine the chip in which the word is stored. Okay. So basically, the MSB bits of the address will be used to select a chip. Very simple. And what is low order memory interleaving? Low order memory interleaving means low order bits of the address. They will be used to select a chip. So you can see low order memory interleaving. It uses the low order, means least significant bits of the address to determine which chip will be selected. Okay, to determine which chip the word is stored in. So these are the two memory interleaving. These are the standard memory interleaving, high order and low order. Very simple. High order memory interleaving, low order memory interleaving. Let's see one example. We have already discussed this in the previous lecture. You can watch the previous lecture. There we have already seen this with many examples. But let's see one more example. Okay, consider this example. Assume you have 32 by 32 memory built out of 4 by 32 chips. Assume there is word addressable memory. Okay, they are word addressable memory. First of all, you tell me, is this example of vertical expansion or horizontal expansion? This is example of vertical expansion or horizontal expansion. You have 4 by 32 chips. This is what you have. Okay, 4 by 32 chips. These are the chips that you have. Okay, using these chips, what you want to design? You want to design 32 by 32 chips. This chip you want to design. Okay, clear? So this is the example of vertical expansion. Why this is the example of vertical expansion? Because you can see number of lines are changing. Number of address lines are, number of address locations are changing. Number of address locations are changing. You can see. Okay, on every location there are 32 bits. That is not changing. On every location you have 32 bits. That is not changing. Remember one thing, that assume that the memory is word addressable. Okay, you can see that memory is already given to you word addressable. Word addressable. Okay, so the memory is actually word addressable. On every address, on every address you will find one word, or I can say that one, for every word we have given one address. Very simple. So in simple words, okay, because remember, this is not changing the size of, I can say, every location. On every location you have 32 bits. Here also on every location you have 32 bits. That is not changing. So overall, basically I can do like this, that you have 4 word chips. Okay, yes or no? Can I say you have 4 word RAM chips? In simple words, I can say you have 4 word RAM chips, but you want to design 32 word RAM chips. But this is what you want. This is what you want. So this is the example of vertical expansion. This is the example of vertical expansion. Here you have 4 addresses. I can say here you have 4 addresses and you want total 32 addresses. Okay, yes or no? So very simple. So this is your vertical expansion. Now let's see. First of all, what you have, these chips, what chips you have? Tell me what we have, what chips we have. Let's discuss them. First, let's discuss what chips we have. So remember, we have these chips. These are the chips that we have. In these chips, tell me how many address lines are there? How many address pins are there? The chips that you have, in these chips, how many address pins are there? Let me know. How many address pins you have? Total 2 address pins. Because remember, total 4 locations are there. Total 4 word are there. Only 4 word are there. Or I can say 4 addresses are there. Okay, so I can say that 2 address pins you have, right? Yes or no? I can say A1, A0. These are the 2 address pins you have. Similarly, how many data pins you have? How many data pins you have? 32 data pins you have, right? Okay, 32 data pins you have. 32 data pins. 32 data pins, D31 to D0. These are the 32 data pins. What else you have? There is a chip select. There is a chip select. There is a write enable and read enable. So this is the chip that you have. Is this clear? So remember the chip that you have. These are the chips we have. These are the RAM chips that we have. Now let me tell you that this chip, this you can also call it module, memory module. You can call it memory chip. Some people, they call it memory module. You can also call it memory bank. Okay, all these things are same. Is this clear? Memory chip, memory module, memory bank, all these things, all these words, they are basically same. Okay, so this is the RAM chip that you have. So remember, in our RAM chip, only 2 address lines are there. Yes or no? Only 2 address pins are there. Agree? In our memory chip, there are only 2 address pins. We have only 2 address pins. Those are A1, A0. These are the address pins. Now what we want, what we want we want 32 word memory chip. This 32 word chip you want. So tell me, if you want 32 word chip, then what is the address size? How many bits in the address? Address will contain how many bits? Total 5 bits. Yes or no? Okay, so total, remember, I need 5 address pins, or I can say total I need 5 address lines. Total 5 address lines I need. Okay, but on my chip, the chip that are available to me, how many address pins they have? The chip that is available to me, that has only 2 address pins. Yes or no? And total how many address pins I want? I want total 5 address lines. Okay, is this clear? Now first of all, you tell me how many chips I need if I want to create. I have 4 word chip. I have 4 word chips. From these chips, if I want to create 32 word chips, then how many chips I need? Tell me, how many chips I need? I have 4 word chip and I want to create 32 word chip. Then how many chips I need? Then you can see 32 divided by 4, that is 8. So total 8 chips needed. You need total 8 chips. Now, these 8 chips, let me call them from M0 to M7. Okay, let's call them M0, M1, M2, and so on, M7. Okay, is this clear? So I'm calling them these. So these are the chips that are needed. Very simple. Is this clear? Now, so what I will do now, total, remember these are the chips. These are the 8 chips that I need. Okay, is this clear? Now what I will do, I have total 5 bits. Remember, I need total 5 address lines. So what I will do, these are the 5 address lines: A4, A3, A2, A1, A0. Now what I will do, how I will make the connection. Okay, notice how I will make the connection. Total I have 8 memory chips. Yes or no? Total I have 8 memory chips: M0, M1, M2, and so on, total M7. So these are the chips that I have. Okay, and these are the address lines that I need. I need total 5 address lines. Okay, in my chip there are only 2 address lines. This chip has only 2 address pins. This has only 2 address pins. Okay, there are only 2 address pins on every chip. On every chip there is 2 address pins only. Now what to do? First of all, you tell me, if you have total 8 chips, then how many bits are needed to select one of them? First, what I will do, I will decide which chip contains my word. See, if the CPU will generate some address, CPU will generate 5-bit address that you already know. Okay, because this is what I want. This is what we want. So CPU, what the CPU will do? CPU will generate a 5-bit address. 5-bit address CPU will generate. Okay. Now what I will do? When the CPU will generate some address, then first I will decide which memory chip to access. Okay, CPU will generate some address, then first I will decide which memory chip to access. You tell me, if there are 8 memory chips, then to decide one of them, which one of them I want to access. So then how many bits I needed? I want to decide one of them. I want to choose one of them. There are total 8 chips. I want to choose one of them. Then how many bits I need to decide one of them? That is 3 bits. Yes or no? So I need 3 bits. Very simple point that, okay, in this basically 3 bits are needed. Please understand that 3 bits, or I can say 3 lines. 3 lines will decide. Okay, remember 3 bits, or I can say 3 lines, 3 address lines. So they will decide. 3 bits decide which chip to access. Yes or no? Which memory module to access. Module to access. So this is the point. Okay, so out of these 3 bits, or I can say 3 lines, they will decide which memory chip to access. Is this clear? Now here comes the concept of high order and low order. What is that? Now tell me, what is high order memory interleaving? Let me know. What is high order memory interleaving? What is that? Memory interleaving. What is that concept? High order memory interleaving. In this concept, what we do? In this high order memory interleaving, what we do? We use the high order bits of the address to select the memory chip. Okay, so understand this, that in this what we do, in this high order memory interleaving, what we do? We use the high order bits. We use the high order bits. High order bits means those are, I can say, MSB bits of address to choose one of the chip. Okay, to activate one of the chip, to select a chip, basically. Okay, to select a chip, to select a memory chip. Okay, is this clear? Very simple point. So this is the idea. So remember, in this high order memory interleaving, what you will do? These 3 bits you will use. So these 3 bits, what they will do? They will be used. These will be used to select a chip. They will be used to select a chip. Okay, so they will just be used to select a chip. What about the remaining? What about the remaining 2 bits? Using these 3 bits, I have selected a chip. Let's assume I have selected this chip. Okay, using these 3 bits, I have selected this chip. I have selected this chip. Then what the remaining 2 bits will do? The remaining 2 bits, they will choose within this module. Okay, yes or no? Within this module, which word to access? Yes or no? Is this clear? Remember, using these 3, I will choose one of the chips. One of the chips I will choose. So they will be used. These 3 will be used to select a chip. I am selecting a chip using these 3 bits. Okay, using these 3 bits. Let's assume this chip is selected. This chip is selected. Now, these 2 bits, what they will tell me? These 2 bits, please tell me. These 2 bits, what they will do? Within this chip, there are total how many words? Tell me. In this chip, how many words are there? In this chip, there are 4 words. Okay, yes or no? There are 4 words. So remember, these 2 bits will decide within the chip which word to access. Within the chip, which word to access, which location to access. Is this clear? Which address location to access? Please tell me, did you understand? Okay, so remember, very simple. These three, okay, these MSB bits, these high order bits, they will be used to select a chip because there are total 8 chips. So what I will do, these 3 bits I will use to select a chip. One of the chips will be selected. Let's assume this chip has been selected. Then what I will do, using these 3, I have selected this chip. Now what I will do, now within this chip, there are total 4 locations. In this chip, there are total 4 locations. So which location you want to access, that will be decided by these 2. Okay, so these 2 will decide within this chip which location to access, which address location to access. Okay, so this is your high order memory interleaving, because high order bits are used to select a chip. You want to select a chip, then you are using the MSB bits of the address. So this is the idea. Okay, now how to do this? Very simple. You are using these 3 bits, right? These 3 bits you are using. So what I will do, you can do like this. For example, if all of them are 0, okay, if all of them are 0, then let's assume this memory chip should be activated. Okay, activated memory chip. On this side, I am writing activated chip. Activated chip. So you can see, if I make all of them 0, these 3 bits, if I make them 0, then this chip will be activated. Okay, if I make them 0, 0, 1, you can put anything here, you can put anything here, then this M1 will be activated. Okay, if I put like this, then M2 will be activated. Is this clear? And finally, when M7 will be activated, tell me. Finally, when M7 will be activated, if I put 1, 1, 1, then here this memory chip will be activated. Is this clear? Please tell me. So you can see in the address, this is your address, right? This is the complete address. In this complete address, if these MSB bits, if these are 0, 0, 0, then this chip will be activated. Okay, these 3 bits, if they are 1, 1, 1, then this chip will be activated. If these 3 bits, these MSB bits in this address, this is the address, this is the address. In this address, if these high order bits, if they are 0, 0, 1, then this memory chip will be activated. Then you will access this memory chip. Very simple. So this is the complete idea. I hope you understood. Is this clear? Please tell me. Is this clear? Let me know. So tell me, which addresses will map to M0? You tell me which addresses will map to M0. Now I want the addresses which will map to M0. Tell me. Which addresses are going to map to M0? Okay, so to M0, just notice, if I ask you, for example, which addresses map to M0, if this is my question, let's assume that my question is, which addresses, okay, which addresses map to M0, map to, or I can say point to M0. So tell me, which addresses will map to M0? Very simple. M0 means they must be 0, right? Yes or no? All of them, they must be 0. That's it. Okay. they must be 0, because you can see when they are 0, then I can say AM0 is activated. In this situation, AM0 is activated. Okay, so very simple. Now, very simple that here you can put anything, here you can put anything. Okay, now you can just notice that from here, now you can just notice that basically 0, 0, 0, 1, 1, 0, 1, 1. Okay, this is same. This is same. So finally, I can say that these addresses will map to AM0. Okay, these are the addresses. For these addresses, you will access AM0. Very simple. Okay, for these addresses, you are going to access AM0. So remember, for these addresses, I can say for addresses 0, 1, 2, 3. For these addresses, what you will do? For these addresses, memory module AM0 will be activated. Memory module AM0 will be accessed. Okay, activated and accessed, I can say. Activated and accessed. Is this clear? So they can ask you for any module. What about the next module? So remember, in this AM0, these addresses are there. Which addresses? 0, 1, 2, 3. These addresses. In AM1, what addresses will be there? In AM1, there will be 4, 5, 6, 7. In AM2, what addresses will be there? In AM2, there will be 8, 9, 10, 11. In AM3, what addresses will be there? In AM3, there will be 12, 13, 14, 15, and so on. Tell me about AM7. Which addresses will be there in AM7? Tell me about AM7. Please tell me. In the AM7, which addresses will be there? I think 31, 30, 29, 28. Yes or no? These addresses will be there in AM7. I hope you understood this complete thing. So can you notice that in this high order memory interleaving, can you notice that in every memory module, you are getting consecutive addresses? Consecutive addresses are within a module. Consecutive addresses within a module. Within a module, you have consecutive addresses. Yes or no? Within a module, you have consecutive addresses. So remember, these are addresses. Okay. What are these? These are addresses. These are addresses. Okay. All of them. They are addresses. These are addresses. Right? Yes or no? So very simple. So you tell me the conclusion. Just tell me the conclusion. When you have high order memory interleaving, whenever you have this high order memory interleaving, basically, when I used to select a chip, to select a memory module. Okay. So when I do this, then this will be called high order memory interleaving. Then this will be called high order, because you are using the high order bits of the address. This is your entire address, and you are in this address, you are using the high order bits of this address to select a chip. Okay, to select a chip. So this is called high order memory interleaving. And in this high order memory interleaving, what happens? What happens in this high order memory interleaving? Consecutive addresses is where you will find. If you want to find consecutive addresses, then where you will find consecutive addresses available within a memory module. Yes or no? Consecutive addresses can be found within a memory module. Available within a memory module. Yes or no? Within a memory module. I hope you understood. Okay, so remember, within a module, you can find the consecutive addresses. If you look any module, okay, for example, if you want these consecutive addresses, these 3 consecutive addresses, if you want, then you can get them within a module. If you want these 2 consecutive addresses, you can find them within a module. Okay, so remember, consecutive addresses are available within a module, unless the corner cases, the corner addresses, right? Of course, For example, if you want 3, 4, then you cannot get them within a module, right? But you are understanding my point. Did you understand the point? The point is that in high order memory interleaving, within a module, you have consecutive addresses. Okay, in simple words, this is what I can say in simple words, that in high order memory interleaving, tell me what we have in high order memory interleaving. In this high order memory interleaving, I can say within a module, you have consecutive addresses. Within a module, if you look at any module, within a module, we have consecutive addresses. We have consecutive addresses. Okay, is this clear? Within a memory module. So this is the idea. Is this clear? Just read this statement and tell me, did you understand this? This is your GATE exam question. Let me tell you. This is GATE 1991 question on your screen, whatever you can see. This is your GATE 1991 question. In high order memory interleaving, within a memory module, we have consecutive addresses. You can find the consecutive addresses within a memory module. Okay, consecutive addresses you can find within a memory module. Is this understood? Please tell me. Okay, so quite simple. Yes or no? Very simple. Now you tell me how you will make the connection. How to make the connections? Basically, these 3 bits you are using these 3 bits to select a chip. Okay, these 3 bits you are using to select a chip. So how you will make the connection? You will use a decoder, right? Yes or no? You will use a decoder. So now I am telling you the implementation. Let's see the implementation. Let's see the implementation. The implementation is like this. Okay, these 3 bits you are using to select a memory chip. To select one of them, these 3 bits you are using. So what you will do? You will basically apply them to a decoder. Okay, you will take a decoder. This decoder you will take, very simple. Okay, so this decoder you are going to take. This is the idea. This decoder you will take, and these 3 bits that you have, you will apply them. Okay, you will apply them. Very simple. So what you will do? This is what you are going to do. Let's see. Okay, so something like this. So basically you will take a decoder, I1, I2. Okay, so there will be, this will be 3x8 decoder. Yes or no? This will be a 3x8 decoder. This will be a 3x8 decoder. These lines you will connect to what? Tell me. This you will connect to chip select of M0. Yes or no? Basically this you will connect to chip select of M0. This you will connect to chip select of M7. This you will connect to chip select of M6. This you will connect to chip select of M1 and so on. Right? Yes or no? This you will connect to chip select of M2 basically, or I can say like this. This you will connect to chip select of M2. Okay, understood? So this is the idea. This you can connect to chip select of M1. Okay, so quite easily you can see this you can connect to chip select of M7. Okay, chip select of M3, M4, M5. Okay, understood? Is this clear? Now actually there are 2 things. There are 2 situations. You tell me. There are 2 situations. If chip select is active low, then what will happen? And if chip select is active high, then what will happen? Okay, basically we are looking at implementation, right? Yes or no? This implementation we are looking at. Okay, we want to see the implementation of vertical expansion. This is what we want. The actual implementation of vertical expansion, this is what we want to discuss. Okay, the case 1, what they can do, they can give you this case that chip select inputs are active low. inputs are active low, they can give you this. Okay. So if chip select inputs are active low, then what you will do? If chip select inputs are active low, then in this situation, which decoder you will use? In this situation, which decoder you will use? Tell me. Because remember, this is vertical expansion. We need a decoder. So this is the case one. Okay. Chip select inputs are active low. In this situation, you will use active low decoder. Yes or no? Yes or no? So in this case, we use active low decoder. Active low decoder. Okay. What we use? We use active low decoder. This is also called NAND decoder, right? Correct. This we have seen in the digital logic. This is called NAND decoder, or you can say this is active low decoder. So when chip select, when these inputs are active low, then what we will do? Then we will use active low decoder. Okay. So again, I'm telling you, what is this active low decoder? Active low decoder, or I can say this is your NAND decoder. Even though we have seen this in digital logic, but let me just quickly tell you what is the block diagram for this active low decoder. The name itself is telling you active low. When it is active, it is low. Okay. So it is like this. When it is active, it will be low. When it is active, it will be low. Okay. So this is your active low decoder. The block diagram, let me tell you, that is something like this. See, either you can simply say that it is active low decoder. Either you can explicitly say that this is active low decoder. Correct. Okay. So this is what you can say. Let's assume this is 2x4 decoder. So either you can do like this. You can simply say that this is active low decoder. Okay. 2x4 decoder, active low decoder. Or what you can do, or you can put this bubble. Okay. Here you can put this bubble. Do you remember? In digital logic, we have already seen. Do you remember? Okay. This bubble will indicate active low decoder. Now you can say here decoder. Okay. You can just simply say that this is decoder. But this bubble indicates active low decoder. Yes or no? These bubbles, they will indicate active low decoder. Tell me, is this clear? Okay, this bubble indicates active low decoder. Bubble indicates active low decoder. Understood? Is this clear? So remember, either you can use this block diagram. I'm telling you active low decoder. Okay, so either I can say active low decoder, or I can do like this. This bubble will indicate active low. Very simple. So in the active low decoder, actually what happens? If I give you this active low decoder, okay. If I give you this active, remember this bubble simply indicates active low, nothing else. Nothing else. This simply indicates active low decoder. Okay, this bubble only indicates active low decoder. Nothing else. Is this clear? So you tell me. So let's assume this is your decoder. This is I0, I1, means this is LSB. And this is a MSB. Okay. And I'm writing Y0, Y1, Y2, Y3. Okay. So this is your active low decoder. Now you quickly tell me. If I apply 0, 0, then what will be the output here? What will be the output if I apply 0, 0? This is active low decoder. This bubble indicates active low. This means active low. So if I apply input 0, 0, then it simply means that this will be 0. This will be activated. Basically, I can say this line will be activated. So in this situation, this will be 0, all other will be 1. Okay. If I apply, for example, this, if I apply, remember MSB is 0. MSB 0, LSB is 1. So in this situation, this line will be activated. This actually will become 0, all other will become 1. Okay. So very simple. Similarly, if I apply, let's assume if I apply this one, then it simply means that this line will become activated. This will become 0, all other will become 1. So this is the idea. And finally, I can say, if I apply 1, 1, then this will be 0, all other will be 1. So this is the functionality of active low decoder, remember? And one more thing, if I remove this bubble, then I have to explicitly say that this is active low decoder. Okay, then what I have to tell you? Then I have to give you that it is active low decoder. Okay, now I can say that it is active low decoder. active low decoder. Now I can do like this also. So this is also another representation. This is another representation. Okay. If I don't put bubble here, then I have to tell you that it is active low decoder. This information I have to give you. Is this clear? Now again, very simple. For example, if I apply 0, 1 here, then what will happen? Then this will be 0 and all other will be 1. So this is the idea. I hope you understood. Now, anyway, let's move on. So this is your, now what happens in a normal decoder? Tell me. In a normal decoder means your and decoder. This is your normal decoder. This is denoted like this without bubble. Okay. You don't have to put any bubble here now. Okay. So now you don't have to put any bubble. This is simple your decoder. This is a simple 2x4 decoder by default. This is normal decoder. Okay. Yes or no? This is your by default decoder, or you can say this is a AND decoder. So in this normal decoder, what happens? Quickly tell me. If this is, for example, I0, I1, this I1 simply means MSB, and this I0 simply means LSB. And these are, for example, Y0, Y1, Y2, Y3. Now, in this situation, what will happen? Quickly. For example, if I apply 0, 0, then what will happen at the output? If I apply 0, 0, this is your normal decoder. If I apply 0, 0, then this line will be activated. This will become 1, all other will be 0. Okay. Similarly, if I apply, for example, this, remember MSB is 0, LSB is 1. So in this situation, this line will be activated. Means this line will be 1, all other will be 0. Okay. And if I do this, this line will be activated. Means this line will be 1, all other will be 0. And finally, if I apply 1, 1, then this line will be 1, all lines will be 0. Okay. Let's move on now. Now let's move on. So we have seen what is the decoder. Both of them we have seen. Now you tell me. Okay, now we are discussing the case 1. What was our case 1? Chip select is active low. Let's assume chip select is active low. Okay, so this is what I have. Let's assume chip select is active low. In this situation, what to do? So these are the chips that you have. Remember, this is your M0. This is your M0 chip. Okay. Then there is M1 chip. There is M1 chip. And so on. There is a M7 chip. Okay. So these are the chips that you have. Now let's assume that this chip select is active low in all of them. In all of them, chip select is active low. Okay. I'm assuming chip select is active low. So this is what I'm assuming. You tell me how many address pins are there? How many address pins are there? How many address pins? This chip, how many address pins this chip has? Only 2 address pins, right? Yes or no? There are only 2 address pins. Remember, there are only 2 address pins. Okay, so please understand that you have only 2 address pins. Here there are 2 address pins. Similarly, there are 2 address pins here also. 2 address pins. And there are 2 address pins here also. Okay. So like this, these are the address pins. Okay. And now ultimately, because chip select is active low, so what I will do, which decoder I will use? Because chip select is active low, so which decoder I will use? Tell me. Here, chip select is active low. So what I'm going to do, I'm going to use active low decoder. Okay. What I will do, I will use active low decoder. I will use. Remember, this active low decoder I am going to use. So I will put this, there should be total 8. So this active low decoder I will put. This active low decoder I will put. Very simple. Is this clear? Okay. So these three bits, they will decide which chip to select. These 3 bits, they are going to decide which chip to select. Okay. So this is I2, I1, I0. Okay. So very simple. Now this is your Y0, Y1, Y2, and so on, Y7. So this is the idea. Okay. This is your active low decoder, right? Clearly you can see this is active low decoder. Now what I will do, very simple. This I will connect to this pin. This I will connect to this pin, and so on. This I will connect to this pin. Okay. Quite simple. Now you just tell me, quickly you tell me, Remember, these are active low chip select. The chip select pins, these are active low. So you tell me quickly, if I apply on these three, if MSB bits, this is your address. In this address, if MSB bits, if they are 000, if they are 000, now what will happen? If they are 000, then this is active low decoder, you already know. Okay, this is active low decoder. So now what will happen? If this is active low decoder, this will be 0, all other will be 1, all other will be 1. Now you can easily see only this is 0. So this chip select equal to 0. So which chip will be activated? Tell me. Which chip will be activated? Remember, all the chip select are active low. They will be active when they are low. All the chip select, they are active low. They are active low. You can see this chip select is active low. So when it is active, it will be low. Or I can say when it is low, it will be active. So you can see in this situation, this M0 will be activated. In this situation, this will be activated, right? So I can say this is activated. Okay, this is idle. This is idle. Simple. Yes or no? Similarly, you tell me on this, in this address, if these three MSB bits, if they are like this, for example, if they are, let's assume they are 100. Now tell me, now what will happen? Now what will happen? Means A2 is 1, A3 is 0, A4 is 0. In this situation, what will happen? In this situation, you can notice this line will be 0, all other will be 1. So in this situation, who will be activated? Okay, you can see chip select is active low. What it means? It simply means that when chip select will be 0, it will be active. When it is low, it will be active. So you can see it is low, so it will be active. So here, this will be activated. Okay, this will be activated, this will be idle, and this will be idle. So this is the complete idea. I hope you understood. And finally, you tell me, if I apply, for example, 111, this is your address. In this address, if these high order bits, these MSB bits, if they are 111, then what will happen? This is the active low decoder. So when I apply input 111, then this will be 0, all other will be 1. Now in this situation, what will happen? Then this will be activated. Okay, this M7 chip will be activated. All other chips, they will be idle. So this is the complete idea. I hope you understood. Okay, one more thing I want to ask. Where these two will go? Where these two will be connected? Tell me, where these two will be connected? These will be connected to these two address pins. Yes or no? Everyone has two address pins, correct? Everyone has two address pins. So these two actually will be connected to these address pins. Okay, because these two will decide within a chip, which word to address, right? Yes or no? Correct? Agree or not? Is this clear? Because these two will decide within a chip which location to access. These two will decide within a chip which location to access. Okay, and these three will decide which chip to access. So remember, they will select one of the chips. Now, once a chip is selected, then these will decide within that chip which location to access. Okay, so remember these two pins, they will be connected to these address pins of the memory module. These two address pins. So they will be connected like this. Okay, so that's your chapter. Okay, so you can see this is your high order memory interleaving. Did you understand? Please tell me. Did you understand? Now in this same, one more thing I want to ask, that is, if chip select input is active high, then what will happen? In the GATE exam, if they give you chip select inputs are active high, if this is given to you, in the exam they give you that chip select inputs, those are active high. Now what to do? Chip select inputs are active high. Let's assume they give you. Now don't put bubble, because bubble indicates active low. Okay, bubble indicates active low. So now don't put bubble. Now just don't put bubble. Okay, so you can see. Okay, so this is the idea. Okay, so here you can see chip select, that is active high. So this is your case 2. When chip select, when these inputs are active high, then what we do? Then we use normal decoder. Then we use normal, right? Then we use normal, or I can say active high. Okay, your normal decoder. Normal decoder is by default active high. Okay, so remember, we use our normal decoder. We just simply use the decoder. That's it. Okay, in this situation, we just use the decoder. So you can see these are the chip select. Now what I will do, I will just use the decoder. Okay, so this decoder I will use. Now this is the decoder. That's it. So 3x8 decoder I will use. Okay, so these will be connected. That's it. Okay, so here you have this decoder. So this is your, I can say 0, 1, 2, 7, and this is 0, 1, 2. Okay. So is this clear? So very simple. Now remember, these will be connected to the pins. Now these will be connected to the pins. Okay. Now just tell me quickly. You tell me quickly. Now when I give this 0, 0, 0, now what will happen? When I give this 0, 0, 0 on these three, I can say MSB bits, if they are 0, 0, 0, okay, in this address, this is your address. In this address, if the high order bits are 0, 0, 0, then remember this is your normal decoder. So this will be 1, the remaining will be 0, right? And because chip select is active high, remember, chip selects are active high. You look at chip select, they are active high. All the chip select, they are active high, means when they are high, they will be active. When they are high, they will be active. So you can see this chip select is high. This chip select is high, so it will be active. So you can say that it is activated. Okay, so this will be idle. This will be idle. Okay, similarly, you can see if I give you, for example, let's assume I give you like this. In this situation, what will happen? In this situation, this will be 1 and all other will be 0. So in this situation, this will be activated. Okay, this will be idle. This will be idle. That's it. Very simple. If I give you 1, 1, 1, this will be 1, all other will be 0. So here this will be activated. Okay, all other will be idle. All of them will be idle. That's it. This is your chapter. Okay, and remember, the remaining 2 bits, they will be connected to whom? The remaining these 2 bits, they will be connected to the address lines. Yes or no? They will be connected to the address lines. Okay, address pins of these memory modules. These are the memory modules. Every memory module has 2 address pins. Yes or no? Every memory chip has 2 address pins. So these two chip, I can say, sorry, these 2 lines, they will be connected to address pins of the memory module. Okay, that's it. This is the complete analysis. We have done the complete analysis of high order memory interleaving. But so far, what we have done? So far, we have done high order memory interleaving. Yes or no? Now let's see the low order memory interleaving. The concept you understood, right? Yes or no? Can I say you have understood the concept? Now this is just, I can say, I'm just explaining the concept, but you have already understood, right? Yes or no? Is this clear? Please tell me. Are you confident? Whatever question comes, implementation question comes, or they ask you in which memory module, which addresses are available. Okay, for which addresses you will access which memory chip. This type of questions they will ask you most of the time in the GATE exam. They will ask you this type of question, that for which addresses you will access this memory chip, for which addresses you will access memory chip 1, for which addresses you will access memory chip 7. This type of questions they will ask you most of the time. Okay, now let's see low order memory interleaving. In this, what we do? In this low order memory interleaving, what we do? We use the LSB of address, LSB bits of the address we use to select a chip. Okay, yes or no? So remember what we do here. Now I am telling you the concept of low order. This is the concept. Low order memory interleaving. Low order memory interleaving. Okay, so in this low order memory interleaving, you just quickly tell me which bits I will use to select a chip. Which bits I will use to select a chip? Just tell me. Just quickly tell me which bits I am going to use. So remember low order memory interleaving. What that means? In this, basically, low order bits. Low order bits. What are those? Those are LSB bits. Those are LSB bits. So LSB bits of address. Of address. This is your address. So LSB bits of this address will be used. Will be used to select a chip. To select a chip. Okay, is this clear? So we will use LSB bits to select a chip. So what we will do? Basically, these 3 bits we will use to select a chip. Okay, because there are total 8 chips. So you need 3 bits to select a chip. Total 8 chips you have, right? Yes or no? We have total 8 chips. So because you have total 8 chips, so what you need? You need 3 bits to select a chip. So remember, they will be used to select a chip. To select a chip. Okay. And what about the remaining 2? Once you have selected a chip, using these 3, you can select a chip. Once you have selected a chip, then these 2 will be used to find the location within the chip. Yes or no? Yes or no? Within the chip, which location to access? Within the chip. Once you have selected a chip, see, these 3 will select a chip. Once you have selected the chip, then within the chip, which location to access? Which address location to access? Okay, so this is the idea. Now let's quickly see. So I'm using these three pins, these 3 lines I will use to select a chip. So what I will do, let me tell you, very simple. I'm writing here chip activated. Which chip will be activated? Okay, so when all of them are 0, okay, this can be anything, this can be anything. In this situation, which chip will be activated? Tell me. In this situation, which chip will be activated? M0 will be activated. Okay. Similarly, if this is 001, this can be anything, this can be anything. M1 will be activated, and so on. This can be anything, this can be anything. If this is 111, then M7 will be activated. So this is the idea. I hope you understood. Now, what they can ask you, which type of question they can ask you? They can ask you, what are the addresses in this memory chip in C7? Okay, this type of question they can ask. They can ask which addresses map to memory chip 7. Tell me the answer. Memory chip 7. Which addresses will map to this chip 7? So very simple point. If you want to map to this chip 7, then what you need? Then these must be 1 1, right? Yes or no? These must be 1 1. Okay, clear? Yes or no? So all these addresses, they map to M7. All these addresses, for all these addresses, what you will do? M7 is activated, and for all these addresses, I can say for all these addresses, M7 will be activated and accessed. Activated, and that will be accessed. Okay, is this clear? So what are these addresses? Tell me quickly. What are these addresses? Anyone? For these addresses, remember, when this is 111, because these are the 3 bits I will use to select a chip. These are used to select a chip. So for these addresses, M7 will be activated and it will be accessed. So quite simple. You can do 111. Okay. You can put 00 here. You can put 01 here. You can put 10 here. You can put 11 here, right? This 11 is fixed. So what is that? For example, this is 7. What is this one? What is the next one? That is 15. What is the next one? Tell me. That is 23. Okay, that is 23. And the next one is 31. So these addresses, for these addresses, what will happen? These are the addresses in M7. Okay, these are addresses in M7. Clear? For these addresses, M7 will be accessed. Okay, if the CPU will generate these addresses, then this chip will be accessed. You will access this chip for these addresses. I hope this point is clear. Now see something beautiful. What will happen? Because you are using these low order bits. Okay, because I'm using these low order bits, now something, what will happen here? I'm using low order bits, right? these low order bits. So now what will happen? See, this is your, which addresses this M0 has, which addresses M1 has, which addresses M2 has, tell me quickly. M3 has, and so on. M7 has. Tell me. So actually this will happen. See, the address 0 will be, for address 0, this M0 will be activated. Okay, for this 0, when the CPU will generate address 0, means all 0, 0, 0, 0, 0, 0. When the CPU will generate this address, then this memory chip will be activated and it will be accessed. Okay, then you will access this memory chip. So this is what I'm saying. So remember, in this M0, this address 0 is available. Okay, next address is available in which memory chip? Tell me. Next address is available in which memory chip? In which memory chip next address will be available? Next address will be available, because remember, okay, see, A4, A3, A2, A1, A0. Just look at the addresses. See, this address, if you look at this address, then which chip activated? So here you can see M0 is activated. For the next address, who will be activated? You can see M1 will be activated. Okay, for the next address, M2 will be activated. For the next address, M3 will be activated. Okay, understood? Like this. So very simple, right? So you can see this address 0 is available in M0, address 1 available in M1, next address available in M2, next address available in M3, then and so on. This address will be available in M7. This address will be available here, this address here, next address here, next address here, and so on. This address here. Is this clear? Please tell me. Let me know. Is this understood? Next address available here. Okay, and so on. Next address available here, next here, next here, next here. And finally, you can see this 31. Okay, and you can just check. I think this will be, yeah, 24, 25, 26, 27, and so on. Is this clear? Please tell me, did you understand? Okay, so this is what happens in the low order memory interleaving. In the low order memory interleaving, where are the consecutive addresses available? Where are the consecutive addresses available? Like these consecutive addresses, these are available where? These are available across the modules or within the module. Tell me. They are available within the module or across the module? Let me know. In low order memory interleaving, tell me, in low order memory interleaving, I am asking this, in low order memory interleaving, consecutive memory addresses are available. Consecutive memory addresses are available within a module. Can I say within a module, or can I say across the modules? See, these are the consecutive memory addresses. These three addresses, they are consecutive addresses. These are consecutive addresses, but they are available across the modules. Yes or no? So you can see consecutive memory addresses are available across the modules. Across the memory modules, not within a module. Memory modules, not within a module. Not within a module. Okay, understood? So that's it. So this is the point. So consecutive memory addresses, they will be available across the memory modules. They are not available within a module. This is your GATE 1991 question. I will show you, don't worry. Okay, this question on your screen, whatever you can see, this has come in GATE 1991. I will show you. Okay, so is this understood? Low order memory interleaving, that you understood or not? Please tell me. Okay, so this is the simple idea. Now the implementation you can do, right? Okay, the implementation is quite easy. What you will do? The implementation, let's look at the implementation that you can easily do. What are the two cases for implementation? For implementation, what are the two cases? One case is when you have active low chip select, when you have active low chip select, or you have active high chip select. Okay, here you can see you have active high chip select. So if you have active high chip select, then which decoder you will use? Tell me which decoder you will use. You can see you have active high chip select, active high chip select. The chip select is active high. So if you have active high chip select, then which decoder you will use? You will use normal decoder. Okay, you will use the normal decoder. 3x8 normal decoder you can use. Okay, just use this decoder. These three will be used to select a chip. Okay, they will be used to select a chip. Simple. They will be used to select a chip and so on. Okay, very simple. And what I will do, this connection I will make to the chip select. Simple. This connection I will make to the chip select. Okay, very simple. That's it. So this is the idea. Very simple. And what about these two where they will be connected? What about these two lines? These two lines where they will be connected? See, using these three, you can select a chip. After selecting a chip, using these two, you can select within a chip which location to access. Okay, so they will be working. Their work will happen within a chip. So remember, these two, they are connected to these two address pins. Every chip has two address pins. Yes or no? Every chip that has two address pins. Every chip has two address pins. So it will be connected to these address pins. So that's it. This is your complete implementation. And if you have active load chip select, then what you will do? If you have active low chip select, tell me. If I have active low chip select, the only thing is if I have active low chip select, means bar, just put bar here. So if I have active low chip select, now what to do? Now just take a active low decoder. Okay, now just put bubble here. Now just take active low decoder. That's it. No other changes. So this is your implementation. Okay. Now let's move on. So this is your complete chapter. I hope you understood all these things. So we have seen high order memory interleaving. Look at this. In the high order memory interleaving, within a module, you have consecutive addresses, right? Look at this. High order memory interleaving. Within a module, you have consecutive addresses. Within a module, consecutive addresses. Within a module, consecutive addresses, and so on. Okay, so this example we have seen. If you look at this, okay, total 8 modules. So this example actually we have seen. This is your address. Address is 5 bits. You can see from these 5 bits in this high order memory interleaving, what I will do, these 3 bits we will use for selecting the module. Yes or no? High order memory interleaving. So MSB bits of the address. This is your address. In this address, the MSB bits, these 3 bits we will use to select a module. And these 2 bits we will use for within the module. Okay, within the module. You can see in module, within the module, which location to access. So this is the idea. Now let's move on. Low order memory interleaving, that also we have seen. You can see in this low order memory interleaving, can you notice within a module, you don't have consecutive addresses. Look at this module. You don't have consecutive addresses. Where you will find consecutive addresses, they are across the modules. You can see address 0, address 1, address 2, address 3, and so on. Okay, so this is your low order memory interleaving. In this low order memory interleaving, what we will do? We will use the low order bits of the address. This is your address, 5-bit address you have. Okay, so in this address, the low order bits you will use to select a module. Okay, so these 3 bits you will use to select a module, and these 2 bits you will use for within the module. You can see in a module which location to select. Okay, so this is the idea. So this is your memory interleaving. I hope you understood. So 2 type of memory interleaving we have seen: high order memory interleaving, low order memory interleaving. In the high order memory interleaving, within a module you have consecutive addresses. In low order memory interleaving, the consecutive addresses are available across the modules. Okay, you can see consecutive addresses, they are available across the modules. So this is your complete topic that we have seen. Let's solve this question. This GATE exam question, let's solve. This is GATE 1991 question. Tell me the answer. This is GATE Computer Science 1991 question. In interleaved memory organization, consecutive words are stored in consecutive memory modules. This will happen in which interleaving? See, look at this. Consecutive words are stored in consecutive modules. Consecutive addresses are available in consecutive modules. This will happen in low order. Yes or no? Read the statement carefully. Consecutive words are stored in consecutive memory modules. Yes or no? Look at this. Read the statement carefully. Consecutive addresses are stored in consecutive modules, consecutive memory modules. So this will happen in low order memory interleaving. This will happen in low order memory interleaving. And look at this. Consecutive addresses are stored within module. Consecutive addresses are stored within a module. This will happen in which? This will happen in high order memory interleaving. Please tell me, did you understand this question? Let me know. Let me know, is this clear? This question is clear to everyone? You clearly understood, right? What this question means? We have already seen low order memory interleaving, high order memory interleaving. These concepts we have already seen. So this question makes sense to you? Agree or not? You understand this question very clearly, yes or no? In interleaved memory organization, consecutive words are stored in consecutive modules. This will happen in low order memory interleaving. And consecutive words are stored within a module. This will happen in high order memory interleaving. So this is your GATE 1991 question. Yes or no? Understood? Please tell me. Let's move on now. Let's solve this question. This is GATE Computer Science 2023 question, latest question. Okay. So this is your GATE Computer Science 2023 question. Read the question and tell me the answer for this question. This question is based on memory interleaving. The implementation is given to you. Now let's solve this question. This is quite easy. Let's solve it. So notice what this question is saying. A 4 KB byte addressable memory is realized using 4 1 KB memory blocks. Okay, in this question, look at this. This question is saying that using 1 KB blocks, memory blocks. Okay, 1 KB blocks. Using 1 KB memory modules or blocks. What you have done? What you have designed? What you want to design? You want to design 4 KB memory blocks. 4 KB memory blocks. First, you tell me, is this example of vertical arrangement or horizontal arrangement? Tell me. Using 1 KB memory blocks. You have 1 KB memory blocks. Using them, you want to design 4 KB memory blocks. Then this is example of vertical arrangement or horizontal arrangement. This is your vertical arrangement, right? Because you want to increase the number of address locations. Okay, so this is your vertical arrangement. You are increasing the number of locations. Total how many locations that you are increasing? Yes or no? Here how many locations? Tell me, here how many locations? Here you only have 1K location. Yes or no? But here you have 4K locations. So you are basically increasing. Okay, here you have 1024 locations. These many addressable locations. Addressable locations. Because remember, the memory is byte addressable, that is given to you. This word, byte addressable, this is already given to you. So you can see you have 1 KB, memory is byte addressable. So you can see we have 1024. These many locations you have, addressable locations. And how many we want? How many we want? We want these many. We want 4 times. Okay, 4 times locations we want. Yes or no? So these many locations we want. 4K locations we want. We want total 4K locations. Okay, 4096. You can say 4096. You can say 4096. These many locations you want. Is this clear? So this is the example of vertical arrangement. Okay. Now let's read the question carefully. So you want to implement 4 KB memory. using 1 KB blocks. So tell me how many chips will be needed. Now tell me how many chips will be needed. Tell me, if you want to do this, then how many memory modules will be needed? So very simple, 4 KB divided by 1 KB. What you will get? You will get 4. So 4 memory modules needed. 4 memory modules needed. Yes or no? Is this clear? So you need total 4 memory modules. That is already given to you in the question. You don't have to calculate, but I'm telling you. So you can easily see that 4 modules are used. Okay, 4 memory modules. This is 1 KB memory, 1 KB memory, 1 KB memory, 1 KB memory. So these are the 4 memory modules. Now the question is saying that 2 input address lines. Okay, now see something interesting. First you tell me how many address lines you need. How many address lines you need? Tell me. Tell me how many address lines you need. See, using 1 KB modules, using 1 KB chip, you want to create 4 KB chip. This is what you want to create. You know that 4 chips will be needed. Now, in these chips, if you look at, then there are total 10 address pins. Yes or no? There are total 10 address pins. Correct? In these chips. These are the chips, 1 KB chips. In these chips, there are 10 address pins are there. But these we want. Okay. These we want. So how many address pins how many address lines? Tell me. Total how many address lines? 12 address lines. Yes or no? So there will be 12 address lines. Simple. Okay, so remember there will be 12 address lines. Total, you have 12 address lines. And using these chips you want to implement. In these chips you want to use, and these chips have only 10 address pins. Okay, you already know 4 chips you need. That you already know. Okay, so you already know that you need total 4 chips. Okay, 4 chips total you need. This is the 4th chip. Okay, so these are the 4 chips you need. Or maybe if, see what I can do, I can make diagram like this. Small diagram. So 4 chips you need. Very simple. These are the 4 chips you have. Every chip only has, remember, 10 lines. Okay, so remember there are 10 address pins. So every chip has only 10 address pins. You can see this also has 10 address pins. Every chip has total 10 address pins because all of them are 1 KB chips. This is 1 KB chips. This is 1 KB chip, 1 KB chip, 1 KB chip. Okay, is this clear? But what we want? We want 4 KB chip. So we want 4 address lines. So the CPU will generate address of 12 bits. Yes or no? Is this clear? We want 4 KB chip. So we need 12 address lines. So CPU will generate address of 12 bits. So remember, CPU is going to generate this type of address. This type of address. CPU is going to generate this type of address. This address will be generated by the CPU. Okay, is this clear? Please tell me. So this is the CPU generated address. This address will be generated by the CPU. Because this is what we want to implement. We want 4 KB chip. It simply means we need 12 address lines we need. It means 12 bits in address bits, I can say. Okay, 12 address bits. So very simple. So there will be, the CPU will generate 12 bits of address. So this is the address that will be generated by the CPU. Okay, so first what you will decide, tell me. This is your vertical expansion. In this vertical expansion, total how many chips you have? Total 4 chips you have. Okay, these are the 4 chips you have. So first what you will decide? You will decide which chip to select. Yes or no? First you will decide which chip to select. There are 4 chips. If the CPU will generate some address, if I give you some address, then first you will decide which chip to access. Yes or no? CPU will give you the address. Let's assume CPU has given some address, some address CPU has given to you. Now, once you have this address, which is generated by the CPU, then what you will decide? You will decide which chip to access. Okay, I should access which chip. So first you will decide which chip to access. Now tell me, there are total 4 chips and you want to choose one of them. Then how many bits you need? There are 4 chips. you want to choose one of them, then 2 bits are needed. Yes or no? Okay, so you can see from this 2 bits will be used. Okay, 2 bits, or I can say 2 lines, 2 address lines. Remember, I can say 2 bits or 2 address lines. 2 address lines will be used to select a chip. Agree? To select a chip. Okay, is this clear? So very simple. So remember, 2 address lines. Out of these, total 12 address lines you have. Now out of these, 2 bits, or I can say 2 address lines, they will be used to select a chip. Now what this question is saying, read the question carefully. The question is saying that 2 input address lines, these 2, which one? Which are used to select a chip? Tell me, which are used to select a chip? You are using A4, A3 to select a chip. This is interesting, right? Yes or no? You are using A4, A3. They are connected to the chip select port of these memory blocks through a decoder. Okay, is this clear? So remember, in this, if you look at this, then actually what is happening? These 2 are used to select a chip. Okay, is this clear? These 2 are used to select a chip. You are using these 2 address lines. What you are doing? These 2 address lines are used to select a chip. Is this clear? So you can see they are actually connected to the chip select of the memory module. Every memory module has a chip select. This is chip select 0. Let's call it M0. Let's call it M1. Let's call it M2. Let's call it M3. So every memory module has a chip select. You already know this. Okay, so every memory module has a chip select. So you can see these 2 are connected to the chip select. Is this clear? Please tell me. So this is given in the question carefully. This is a beautiful question. Every information is given in the question. Can you see? Can you see every information is given in the question? Like every information is already given in the question. You just have to read the question, understand the question, and solve it. So you can see 2 input address lines. Okay, these 2, which one? A4, A3. These are connected to chip select port of these memory modules through a decoder shown in the figure. Okay, what about the remaining? What about the remaining lines? Tell me, what about the remaining lines? These 2 will select a chip. Okay, these 2 will select a chip. What about the remaining? Please tell me. See, they will select a chip. I can say, look at these 2. They will select a chip. They will select a chip. But what about the remaining? How many remaining lines are there? Just tell me. How many remaining lines are there? Total 10 remaining lines are there. Yes or no? How many remaining lines? Total 10 remaining lines are there. Now you can see, these 2 will select a chip. Let's assume this chip is selected because there are total 4 chips. Now these 2 lines, they will select a chip. They will select a chip. Let's assume this chip is selected. Now in this chip, which address to access? Yes or no? Okay, using these 2, let's assume you have selected this chip. Now in this chip, there are total 1024 locations. In this chip, there are total 1K locations. So which location to access? That will be decided by the remaining lines. Okay, so remember all the remaining lines, if you look, all the remaining lines, all these remaining, they will be connected to the address pins of these memory modules. Is this clear? They will be connected to address pins of these memory modules. So you can see they will be connected to address pins of these memory modules. Is this understood? Please tell me. Okay, so I hope you understood. So remember, I can write here that remaining address lines, what they will do? Okay, remaining address lines will decide within a chip, which, okay, I can say will decide within a chip, which location to access. Okay, is this clear? Within a chip, which location to access. So this is what they will decide. Within a chip, which location. So this is the idea. I hope you understood. Okay, so this is given to you. You can see the remaining 10 address lines. Read the line, read this statement. The remaining 10 address lines, okay, they are connected to address port of these blocks. They are connected to address port of these blocks. And chip select is active high. This is already given to you. Chip select is active high. Tell me, when chip select is active high, then which decoder we use? When the chip select is active high, you can see in this question it is given. Chip select is active high. Then which type of decoder we use? We use a normal decoder, right? Normal decoder we use, correct? Are we using normal decoder? Look at the diagram. Are we using a normal decoder? Yes. Look at the diagram. We are using a normal decoder. We are not using active low decoder. We are using a normal decoder. Okay. So this question, can I say this question is like the revision of whatever we have seen, memory interleaving. In the memory interleaving, whatever we have seen, this question is the complete revision of that concept. Yes or no? Okay, I hope you are finding this question very interesting. This question has given you everything. Diagram is given to you, information is given to you, everything is given to you. The question is also saying that chip select is active high. This information is also given to you. Okay, yes or no? Chip select is active high. So we will use the normal decoder that we have already seen in our lectures. We have already seen this concept, interleaving, memory interleaving, high order memory interleaving, low order memory interleaving. All these concepts we have seen. We have taken a lot of questions. We have done a lot of examples. This question is the complete revision of whatever we have studied. Okay, yes or no? So this is a beautiful question. I hope you can appreciate this question, that this is very well framed question. Every information is available. Okay, now let's come back to the question. So you can see chip select is active high. Okay, so all the information that is given to you. Now let's move on. Now what else is given to you? Now what this question is asking? Look at this question. So this diagram that is given to you, now the question is saying, read the question carefully. The input memory addresses, okay, A11 to A0 in decimal for the starting location of each block indicated by x1, x2, x3, x4 are among the options below. What this question is asking, read this. What this question is asking, this question is asking that for every block, what is the starting memory location? Is this clear? What is the starting memory location? The question is asking for each block, what is the starting memory location, starting location. So what is x1? Tell me what is x1? X1 is the starting address. X1 is the starting memory address in this chip. Yes or no? Let's call it M0 chip, M1 chip, M2 chip, M3 chip. So what is x1? Tell me. What is x1? X1 is starting memory address in memory chip M0. In memory chip M0. Is this understood? Please tell me. What is x1? X1 is what is the starting memory address in this memory chip M0? Okay, in this memory chip M0, what is the starting memory address? Understood? Please tell me. And what is x2? What is x2? In memory chip M1, the starting memory address. In decimal, that is also given to you in decimal. Yes or no? Okay, so did you understand the question? Now this question is quite simple, very simple. Now there is nothing in this question. Now this question is very simple. See, these two, look at these two address lines. they are connected to, okay, just take care. They are connected to the decoder in the same fashion or not. For example, this is MSB, this is connected to MSB or LSB. These small things you should take care. See, these small things you should take care. Did you take care before solving this question? Did you take care that, did you notice this A4 is connected to MSB or LSB of the decoder? Please tell me, did you notice? Did you take care of these small things? You should take care. Okay, you should take care. Basically, you can see A11, A10. Okay, there is, I can say A9 and so on. A5, A4, A3, A2, A1, A0. Okay, what this question is saying? See, the question is saying that there is a decoder. Of course, there is a decoder. This is your decoder. Okay, in this decoder, you can see, in this decoder, this is your, look at this. In this decoder, this is MSB, this is LSB. Okay, in this decoder, and this is 0, 1, 2, 3. This is the decoder, right? Is this clear? All these small things you should notice. This is what I'm telling you. All these small things you should notice. Okay, now the question is already saying that to this MSB, of course, this is MSB, right? This is the MSB and this is the LSB. This is the MSB pin, input pin. This is the MSB input pin of decoder. This is the MSB input pin of decoder. Okay, and this is LSB. Now, what this question is saying that to MSB you have connected A4, and this is what we should do, right? Agree or not? Yes or no? Is this clear? Are you getting my point? Okay, so like this, they have connected. Okay, and what they have done? This is connected to what? Tell me. This Q0, that is connected to what? Tell me. That is connected to M1, chip M1. Yes or no? Chip select of M1, chip select of M0, chip select of M0. Sorry, chip select of M0. Yes or no? Chip select of M0. Chip select of M0. Okay, and this is connected to chip select of M1. This is connected to chip select of M2. This is connected to chip select of M3. So that's it. This is the question. Okay, now let's tell me the answer now. So you can easily see when these are 0, 0, what will happen? Tell me. When they are 0, 0, if I put these two 0, 0, A4, A3, if I put them 0, 0, then tell me what will happen? This is a decoder, right? So in this decoder, this will be 1, this will be 0, this will be 0, this will be 0. Okay, and remember, chip select is active high. This is given to you. Chip select is active high. So which memory module will be activated? Which memory module will be activated? Tell me. If I put A4 equal to 0, A3 equal to 0, if I give them 0, 0, then in this decoder, you can easily see this will be 1, this output will be 1, the remaining output will be 0. So in this situation, remember, chip select is active high. Chip select is active high means chip select is high when it is, sorry, is active when it is high. Chip select is active when it is high. So you can see this is high. So I can say this memory module will be activated. Okay, so M0 will be selected. So finally, this is the point. Okay, A11, A10, and so on. I can say this is A5, A4, A3, A2, A1, A0, A1, A0. Which chip activated? Which chip activated? So if these two are 0, 0, whatever else you take does not matter. Whatever else you take does not matter. If you take, okay, whatever else you take does not matter. If these two are 0, 0, we have already seen from the diagram. From the diagram, we have seen that memory chip M0 is activated. Okay. What happens if they are 0, 1? What happens if they are 0, 1? Then who will be activated? Tell me. If they are 0, 1, then who will be activated? Let me know. So if I put, for example, if I put 0 here, 1 here, means if this is 0, this is 1. Now tell me who will be activated? In this decoder, you can notice, in this decoder, remember this is MSB. Remember this is MSB. Okay, so MSB is 0. Yes or no? MSB is yeah, that is fine. Okay, so you can see MSB is 0, LSB is 1. So in this situation, this will be 1, all other will be 0. No problem. Yes or no? So here M1 will be activated. Correct or not? Here M1 will be activated. Now similarly, you tell me, if this is 1, this is 0. If this is 1, this is 0, then what will happen? Then this will be 1, the remaining will be 0. And finally, you tell me, if both are 1, 1, then what will happen? If both are 1, 1, then this will be 1, the remaining will be 0. In this situation, M3 will be activated. Okay, so you can see in this situation, M1 will be activated. In this situation, M2 will be activated. In this situation, M3 will be activated. Okay, understood? Is this clear? So this is your simple question. Now, just you tell me what is the starting address. Now let's find out X1. What will be X1? X1 means, remember this will be X1. X1 is the starting address in M1, in chip M1. What is X1? Remember in the question, X1, what is that? That is in chip M1. Sorry, in chip M0. In chip M0. Okay, in chip M0, the starting address. The starting memory address. The starting memory address. Similarly, what is X2? That is in chip M1, the starting memory address. What is the starting? Just the question is only asking starting memory address, nothing else. Starting memory address. Okay, so you just tell me in chip 1, in chip M0, what is the starting memory address? So this is your M0, right? Okay, when I put this, then this simply means chip M0. Okay, this simply means chip M0. Now, the starting address, for the starting address, you will make all 0. This will be starting address. So what is your starting address X1? That is 0. Yes or no? Starting address X1, that is 0. So X1 is basically 0. What is X2? What is X2? X2 means chip M1. Chip M1. X2 means chip M1. Chip M1. The starting, for the starting address, you will make all 0. For the starting address, you will make all 0. What is X2? Tell me. What is this value? What is this value? This value is 8. Yes or no? Finally, what about this one? This means chip M2. This will be X3. For the starting address, you will make all 0. Okay, so what is this value? Tell me. This value, that is 16. And finally, you tell me, what about the last one? What about the last one? A3. What is the value of, tell me, X4? What is the value of X4? Let me know. What is the value of X4? For X4, what you need? You need this 1, 1. Okay, you need this 1, 1 for memory chip M3. Okay, so for the starting address, you will make all 0. Now, what is this X4? If you calculate this, then that is 24, right? Yes or no? So what is the answer? The starting addresses are 0, 8, 16, 24. Please tell me, did you understand this question? And did you find this question beautiful? This is really beautiful question. Every information is already given to you. You just have to solve this question. Everything is given to you. The question is only asking the starting addresses, nothing else. The question is not asking anything else. Okay. So in this question, actually, you can easily solve this question. Notice, just notice. What is X1? X1 is the starting address of this memory module. In this memory module, what is the starting memory address? Okay. So in this memory module, tell me, if you want to access this memory module, then what should be A4, A3? Just tell me quickly. If you want to access this memory module, I want to access this memory module. If you want to access this memory module, then A4, A3. they must be what? A4, A3. If I want to access this memory module, then I need this Q0. I need this Q0. Yes or no? If I want to access this memory module, this is connected to Q0 of the decoder. In this decoder, this memory module is connected to Q0. If I want Q0, then what should happen? Then this should be 0, this should be 0. Means A4 should be 0, A3 should be 0. They must be 0, 0. Okay. So you can see. Okay. Is this clear? Now, and so on. So in this situation, these addresses, they belong to this memory module. Let's call it memory module M0. Okay. So these addresses are in memory module M0. Is this clear? Please tell me. So remember, these address, or I can say these are the addresses in memory module. These are the addresses in memory module M0. Okay. Yes or no? So let's do the complete analysis. You tell me what are the addresses. See, the question is asking the starting addresses we have found. The question is asking only the starting addresses. Okay. Yes or no? In this question, it is asking only the starting locations. The question is only asking starting locations. But you tell me what are the addresses in this memory module M0. Just tell me. Basically, find addresses in memory module M0. Find all memory addresses. Find all memory addresses in memory module M0. So what you will do? If you want to do this, then what you will do? Very simple. These are your from A11 and so on, A4, then A3, then A2, A1, A0. Okay. If the question is asking you all the memory addresses, if the question asks you all the memory addresses, what are the memory addresses in memory module M0, then what you will do? Very simple. Just make it 0, 0. Just make it 0, 0. Now you can see, now you can easily do, okay, from all the remaining, you can start from 0, 0. Okay. All the remaining, you can start from 0, 0 to all the way to all of them 1, 1. Yes or no? Is this clear? But remember, it's not like, so can I say answer will be this? Can I say answer will be from 0 to what is this value? Can I say answer will be that? Please tell me. For example, what is this value? Okay, if I make all of them 1. Okay, so whatever, basically, can I say the answer will be this? No. Remember, because for example, you will never have, I can say 15, right? Yes or no? You will never have 15. Are you getting my point? Okay, yes or no? Yes, very good, very good. This is not high order interleaving. Very good. Mikasa, very good. This is not high order memory interleaving. So you will not get consecutive addresses. Is this clear? You will not get consecutive addresses in any memory module. See, these you are using, these 2 bits you are using to select a memory chip. So this is not a high order memory interleaving, right? Yes or no? This is not a high order memory interleaving. High order memory interleaving. So we will not get consecutive addresses within a memory module. Yes or no? Is this clear? So we will not get all consecutive addresses, I can say. All consecutive addresses within a memory module. Consecutive memory addresses within a module. For example, let me tell you, in this M0, which addresses will be there? Okay, I'm telling you addresses in M0. For example, these addresses will be there from 0 all the way to 7. Yes or no? These addresses will be there. these addresses will be there. Agree with me? Do you agree with me? That addresses in M0, I can say from 0 to 7, from 0 to 7 will be there, but 8 will not be there. Yes or no? 8 will not be there. In this M0, you can see 8 will not be there, 9 will not be there, okay, and so on. So for example, I can say 8 all the way to 15 will not be there. They will not be there. Actually, 16 also will not be there. If you look at 16 also will not be there. Okay, so basically, this is the idea. Even 16 will not be there. I hope you understood. Is this clear? Please tell me. So remember, I think till 31, actually these addresses will not be there. These addresses will not be there. Okay, 0 to 7 will be there. Till 31, nothing will be there. What about 32? Tell me, what about 32? Yes, 32 will be there, right? Yes or no? 32 will be there. Okay, 32 will be there. So this is the idea. I hope you understood the idea that you will not get all the memory and so on. Okay, and so on. You understood the idea, right? Yes or no? Because you are using these 2 bits to select a memory. You are using these 2 bits to select a memory module. So remember, this is not high order memory interleaving. So we will not get consecutive memory addresses. We will not get all consecutive addresses within a module. Is this clear? Please tell me. Let me know. This is the complete analysis of this question. So remember, if you look at M0, addresses in M0, then you will see 0 to 7 are in M0. 8 to 31 are not in M0. Okay, 32 is in M0 and so on. So this is the complete idea. I hope you understood. Okay, so this is enough. Please tell me, understood? Let's move on. So this was your GATE exam question. Beautiful question. I hope you loved it. Okay, let's move on. So these are some notes. We have already seen everything. Whatever is written in these notes, we have already seen. Okay, so can I give you these notes as a, I can say, self-study? Because whatever is given in these notes that we have already seen. We have seen high order interleaving. We have seen low order interleaving. All these things we have seen. So you can read. You can read about high order interleaving. You can read about low order interleaving. All these concepts you can read. Okay, let's solve this question quickly. We have 16 by 8 size memory chips. And what we want 32 by 16 memory chip. Now you tell me, is this vertical arrangement or horizontal arrangement? Read the question carefully and tell me, is this vertical arrangement or horizontal arrangement? We have 16 by 8 memory chip and we want 32 by 16 memory chip. So this is both, yes or no? This is combination of both. So remember, here we need to do horizontal plus vertical. Both of them we need to do. Okay, here we need to do horizontal also and vertical also. Here we need to do both the expansion. Correct? Okay, so you just tell me how many chips will be needed. That is the first question. How many chips you will need? That you tell me. How many chips needed? How many chips needed? See, if I ask you total how many chips needed, all you have to do, just divide 32 into 16 divided by 16 into 8. Okay, just do this. This value, whatever is this value, that will be your answer. Just calculate this. That is 4. So 4 chips will be needed. Is this clear? So how many chips will be needed? For that, what you need to do, just divide this by this. That's it. Okay, your answer will be 4. Now, what will happen? So you need horizontally, tell me, horizontally, how many chips you need to put? Horizontally, how many, basically, how many chips? The horizontal arrangement of how many chips you need to do? 2. Yes or no? Very, very simple. So basically, this horizontal arrangement you need to do, this horizontal arrangement you need to do, and this vertical arrangement you need to do. Yes or no? Now tell me, One thing you tell me. So this is the complete thing. I hope you understood. Now, here you can see this is the horizontal arrangement and this is the vertical arrangement. How many address lines will be there? How many address lines will be there? That will be decided by this. Tell me how many address lines? What is the number of address lines? What is the number of address lines? That will be 5 bits. Yes or no? Because there are 32 locations. Because there are 32 locations, so there will be 5 bits. That's it. Okay. How many data lines will be there? That will be 16. This will be the number of data lines. Okay, this will be the number of data lines. Now tell me, do you need decoder? Do you need a decoder? Remember, you need 5 address lines. You need 5 address lines. There will be 5 address lines: A4, A3, A2, A1, A0. Okay, you need 5 address lines. This is what you need. Total 5 address lines you need. Do you need a decoder? What is the size of decoder you need? You tell me. For horizontal arrangement, do you need a decoder? For this horizontal arrangement, do you need a decoder? No. You only need decoder for vertical arrangement. Vertically, you tell me. Vertically, use. Okay, remember, this is like a 1. See, this will act like a 1. I told you. This will act like a 1. This we have already seen. This will act like 1. Like a 1 unit. Okay. Is this clear? Similarly, this will act like a 1 unit. Is this understood? Because this is the horizontal arrangement. So this will act like 1 unit. Yes or no? Is this clear? Please tell me. So remember, how many bits you need to choose which bank to select? Okay, you can say that there are 2 units here. How many bits you need from the address? In this address, how many address lines you need to choose which chip to select? Only 1. Yes or no? Only 1. So what you can do, for example, maybe you can use this. Okay, so you just need a decoder of 1/2 size. You just need a 1/2 size decoder. Very simple. Okay, what we will do, this will connect to, and I told you one thing. How do we do the horizontal arrangement? How do we do the horizontal arrangement? See, basically these 2 chips you will put horizontally. These 2 chips you will put horizontally. Okay. Now there is a chip select here. 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 Now you tell me, I already told you that these 2 chip selects we will connect. And similarly, these 2 chip selects we will connect for horizontal arrangement. Yes or no? Is this clear? This is for horizontal arrangement. So far we have done horizontal arrangement. This is what we have done. So far we have done horizontal arrangement. In the horizontal arrangement, this is what we do. Now what we do? Now we just do the vertical arrangement: A4, A3, A2, A1, A0. So this is your decoder. This is a 1/2 decoder. This is a 1/2 decoder. Okay. So you can do like this. So there will be 2 outputs. You can connect them to chip select here, and another you can connect to chip select here. That's it. Okay. So this is your complete structure. I hope you understood. Is this clear? Please tell me. So like this you can handle. Okay. So this type of questions, if they ask, you can handle. Now let's see this question. This question is from Maurice Mano. Computer System Architecture by Maurice Mano. From this book, this question is taken. Tell me the answer. How many 128/8 memory chips are needed to provide a memory capacity of 4096/16? So how many chips are needed? Tell me. If I ask you number of chips needed, then what you will do? If I ask you number of chips needed, that is very simple. 4096/16, just divided by 128/8. Just divide. What you will get? You will get 2. And what is this? This is your 2 power 7. This is 2 power 12. Okay, so finally what you are getting? Tell me. I think you are getting 2 power 6, that is 64, right? Yes or no? So 64 chips will be needed. Is this clear? 64 chips will be needed. Now you tell me, in the horizontal arrangement, how many chips we need to put? How many chips we need to put horizontally? You tell me. How many chips we need to put horizontally? For that, which you will divide. See, if I ask you about horizontally, notice, if I ask you about horizontally, means horizontally how many chips you will put. Then what you will do? Then just divide this 16 by 8. Okay, don't divide the remaining. Basically, in this situation, just divide this 16 by 8. Is this clear? Horizontally, 2 chips you will put. And what about vertically? What about vertically? For vertically, you divide this 4096, just divide it by 128. That's it. Is this clear? So that will be your, you can see this is 2 power 5, right? Okay, is this clear? 32. So vertically 32 and horizontally 2. You can see total 64 chips. What about the decoder size? What is the decoder size? Tell me. What will be the decoder size in this question if I ask you? Decoder size will be what? Decoder is used for vertical arrangement, right? Yes or no? For vertical arrangement, decoder is used. The decoder that is used for vertical arrangement. So what will be the decoder size? What that will be? You can see total 32. I can say vertically, there are total 32 chips. There are total 32 chips vertically. Okay, so you need 5 by 32 decoder. This decoder you need 5 by 32 decoder. In the address, how many bits you will use to select a chip in the address? Okay, see this question. We are doing the complete analysis of this question. Using these chips, you have created 4096 into 16. These chips you have created. So first of all, how many address lines? You tell me quickly. What is the number of address lines? Number of address lines, that will be 12. Yes or no? That will be 12. Okay, because there are these many locations, 4096. These many locations are there. So number of address lines will be 12. Okay, very simple. Data lines, that will be 16. Number of data lines, that will be 16. Okay. And in these address lines, how many bits will be needed to select a chip? Tell me. In these address lines, in these 12 address lines, in these 12 address lines, how many lines will be needed to select a chip? Tell me. Because you can see vertically there are 32. Vertically there are 32 chips. Okay, vertically if you look at, then you can say 32 levels are there. You have 32 levels. One of them you have to choose. Yes or no? Vertically there are 32 levels. So you have to choose one of them. So in these 12 address lines, basically 5 lines will be used to select a vertical level. Okay, I can say like this. I can say vertical level of chips. So like this. Anyway, so you can solve these type of questions. Whatever they ask you, you can solve it. So read this. This is the complete summary. These are the formula. So what this question is, see, this is the nice summary that if you want to design M by N, this is what you want to design from D by W chips. Okay, from D by W chips. Then tell me how many chips will be needed? Using these, this is what we want to design. This is what we want to design. So how many chips will be needed? Tell me. For that, just divide this by this. Yes or no? So remember, number of chips needed. If I ask you how many chips will be needed, for that you divide this by D into W. That's it. This is the first thing. What is the second thing? Horizontally, how many will be there? Tell me. Horizontally, how many chips you will put? Horizontally, how many chips you will put? That will be N divided by W. Okay, yes or no? Basically, horizontally, see, number of columns. Okay, number of columns, or I can say basically horizontally, how many chips you will need? So that will be N divided by W. These many chips, yes or no? These many chips, N divided by W. And what about the number of rows? What about the number of rows? Means vertically. That will be M divided by D. Okay, so these are the formulas that are given to you. You can just see. Very simple. Let's solve this question quickly. Tell me the answer. Assume you have 1G into 32 memory built out of 32M into 16 chips. Okay. Using these chips, we are creating 1G into 32 memory. Answer the following questions. You have word addressable memory. What you have? You have word addressable memory you have. Okay. The question is asking how many chips are needed. Tell me quickly. This is a standard question from a standard university. The question is saying that 32M into 16. Using these, we are creating 1G into 32. 1G into 32. Okay, this is what we are creating. And remember, word addressable memory you have. Remember, this is word addressable. Okay, if this is word addressable, this is a word addressable. Okay, you have word addressable memory. You have created word addressable memory. So tell me how many address lines? What is the number of address lines? What will be the number of address lines? That will be 30. Yes or no? Because you have word addressable memory. Remember, you have word addressable memory. This is given in the question. It is given in the question that you have assumed word level addressing. Okay. So you can see these many locations. Basically, these many words you have. 1G words you have. Yes or no? Is this clear? Basically, total these many words you have. You have total 2 power 30 words. 2 power 30 words. And remember, the memory is word addressable. The memory, that is word addressable. So number of address lines, that will be 30. How many chips will be needed? That is the first question. So what will be the answer? How many chips are needed? So for that, you just have to do 1G into 32, just divided by 32M into 16. Okay, just divide it. What your answer will be? So 30 to 32 cancel. So it will be 2 power, I think 2 power 6, right? Yes or no? 64. So 64 chips will be needed. So this part is very easy. Just divide this 1G into 32, just divide by 32M into 16. Very simple. Now the question is saying, how many chips are needed to make up one bank? What this means, anyone? What this second option is asking, how many chips are needed to make one bank? One bank. This is horizontally or vertically? What this question is asking? This part B. The part B is asking, how many chips are needed to make one bank? We want one bank. This is horizontal. Yes or no? See, focus on. We want one bank. Okay, to make one bank, how many chips will be needed? So this is your horizontally the question is asking. Here the question is asking horizontally how many chips you will put. Okay, horizontally how many chips you will put. So tell me, basically how many chips will act as one chip? Yes or no? See what option B is asking. Option B is asking how many chips will act as one chip, as a unit. How many chips will act as one chip? This is what the question is asking. See, this is asking how many chips will act like one chip. like a one chip, or I can say one bank, or I can say one bank or one chip. Is this clear? Please tell me. Is this understood? The language of option B, did you understand? Please tell me. The language of option B. How many chips are needed to make up one bank? Means how many chips will act like a one bank, or I can say one unit. Okay, so this is the question is asking horizontally. So for that, what you will do? For option B, what you will do? That is quite simple. All you have to do, just divide this 32 by 16. Just divide this 32. Okay, this 32 you just divide by 16. This is quite easy. So that will be 2. Okay, so 2 chips. So this is your answer for option B. What about option C? How many banks will be there? Now what this question is asking? How many banks will be there? Now what this question is asking? Now this is asking vertically. Basically, vertically, how many levels are there? Okay, vertically. Now tell me, vertically, if you want to find, then what you will do? Just divide 1G divided by 32M. 32M. So what that will be? 1G divided by 32M, that will be 32. So for this question, for option C, answer will be 32. All the options are clear. See, this is a standard question from a university. Okay. Now everything is clear, right? Yes or no? When you are solving this question, or all your concepts are becoming clear or not? Please tell me. Horizontally, vertically, everything the question is asking. Okay, you can answer it. Very simple. Now you tell me about the option D. What the option D is saying? How many bits will it take to make one address? So word addressable memory is given to you. The question is saying word addressable memory you have, and you have 1G words, 2 power 30 words you have. So how many address lines you need? 30 address lines you need. Yes or no? So there will be total 30 address lines, 30 bits in the address. So the answer will be 30. For option D, answer will be 30. Is this clear? The question is asking address will have how many bits? Address will have how many bits? So 30 bits address will have. Okay, or I can say 30 address lines will be there. What about the next? What about option E? Option E is saying that of the bits for part D, means these 30 address lines that you are having, out of them, if you use low order interleaving, if we use low order interleaving, which bits will go to the bank select and which bits will select address within the chip? Okay, so you tell me the answer. What option? See, the question is asking option E. Option E is saying that you have, what you have? Total you have 30 address lines. Total you have 30 address lines. Now, using low order interleaving, we want to use low order interleaving. Okay, so tell me, using low order interleaving, how many lines will be used for bank select? Okay, read the question. Option E, read the question. This is saying that if you use low order interleaving, then how many bits, which bits will go to bank select? Tell me, which bits you will use for bank select? First of all, how many bits you need for bank select? How many banks are there? Number of banks. Tell me how many banks are there? Number of banks. That means basically vertical levels. Vertical levels. How many vertical levels? What is that? Number of vertical levels, that is 32. Okay, so these many banks you have. So how many bits are needed? So 5 bits needed to select a bank. Needed to select a bank. Is this clear? 5 bits are needed to select a bank. Okay, in the low order, which bits you will use? If you have total 30 address lines, there are total 30 address lines. In the low order interleaving, you need 5 bits to select a bank. So these bits will be chosen. Yes or no? These bits will be used. This is what the question is asking. So remember, these will be used for bank select. Okay, using these you will select a bank. So they will be used for bank select. And what about the remaining? They will select location within a chip. Yes or no? Select location within a chip. Within a chip. Okay, so that's it. This is what part E is asking. Did you understand? Did you understand the part E? The part E is asking, if you use low order interleaving, then which bits will be used for bank select and which bits will be used to select the address on the chip. Okay, so this is the answer. So these 5 bits will be used for bank select, and the remaining bits, they will be used to select location within a chip. Okay, so this is your question. These are the answers. You can easily see. For the previous question, these are the answers. Tell me quickly the answer for this. Quickly tell me the answer for this question. This is GATE Computer Science 2009 question. How many 32K by 1 RAM chips are needed to provide a memory capacity of 256K bytes? What is the answer for this question? First of all, you tell me what this means. 32K by 1 RAM chips. What this means? Is this 32K by 1 byte or 1 bit? What is this? Tell me. What is this? This is bit, because I told you that by default, I told you this is how we represent the memory. This is the memory notation. Or I can say this is the memory representation. This we have already seen in our first class. In the first class, we have seen this memory representation. In the memory representation, what we do? We say that number of locations. How many memory locations are there? How many memory locations are there multiplied by number of bits per location. Number of bits per location. Yes or no? Okay, this we have already seen. So very simple. So when I say that 32K by 1 RAM chips, what this means? This means 32K locations are there. Locations multiplied by 1 bit per location. 1 bit per location. Okay, the question is saying how many these chips are needed if you want memory capacity of 256K bytes. Okay, so these many locations. Okay, and 1 byte per location. 1 byte per location. This is what you want. Is this clear? So tell me the answer. How many these chips will be needed if you want this capacity? The answer is very simple. Just divide this by this. So the answer will be, so your final answer for previous question, that will be 256K. K means 2 power 10. Byte means 8. Okay, now you have in bits. And below what you have 32K. So that is 2 power 10 into 1 bit. Okay, now you can divide this. What will be the answer? Okay, just divide this. These two will cancel out. And this will be 2 power. This is 2 power 8, right? So 2 power 8, 2 power 3, that is 2 power 11 divided by 2 power 5. So that is 2 power 6. So that is, I think, 64. So the answer will be 64. Okay, so very simple question. Is this clear? This question has come in ISRO also. This question has come in GATE Computer Science also. And this is very simple question. Okay, what is the most common mistake in this question? Anyone? What is the most common mistake in this question? The most common mistake is students can think that this is 32K by 1 byte. Yes or no? Okay, so students can, this is the most common mistake here. I can say in this question, the most common mistake, what that will be? Most common mistake will be thinking that this is 32K by 1 byte. Okay, this is the common mistake. But anyway, in the first class, I told you that this is the memory representation. We represent the memory like this. number of locations multiplied by number of bits per location. Okay, how many bits are there per location? So you can solve this question very easily. So basically, these are the memory chips you need to use. Using these chips, you need to create a memory capacity of 256K bytes. So how many chips will be needed? Very simple. Divide this by this, you will get your answer, that is 64. This is your option C. Okay, so that's it. Okay, so we have seen everything. I hope you understood all these concepts. Please tell me, everything is clear? Can I say, is everything clear? Whatever we have seen, all the concepts for so far in computer organization, whatever we have seen so far in computer organization, cache memory we have seen. Okay, we have seen all about main memory. Okay, those also we have seen. So far everything that we have seen. And remember one thing, that in our lectures we are solving all the gate questions and many standard questions we are solving. You can see each and every gate question from the topics that we study. Okay, we are solving. So you don't have to basically solve the gate PYQs other than our lectures. In our lecture, we are solving each and every gate PYQ. In the lecture, you will find, okay, after every topic, I'm taking all the gate PYQs. I'm not leaving any single gate PYQ. Whenever I teach some topic, I'm taking each and every gate PYQ of that topic in the lecture. Okay, so when you watch the lectures, then remember you are also covering your gate PYQs of computer organization. Okay, so far everything is clear. Okay, thank you everyone. See you in the next lecture. Okay, thank you.